Okay, well, welcome back, everyone. I hope that you can hear me. No, good morning, good afternoon, good evening, whatever applies. Let's continue with the course. Before I move on with the new material, here is something that you may care about. I hope that you can see it. I posted this file to the course webpage. It is the first problem set. So in case you're taking, excuse me, in case you're taking this course for credit, you should solve any 4 of these exercises. In case you're not taking it for credit, still you're welcome to solve them, needless to say, and you can send me solutions. So I'll be happy to comment on them. At least for the first problem set, I'll see if how much work it's going to be. Anyway, so basically, all the exercises are taken from my book, and there are numbers of the exercises. In some cases, they are modified in a minor way. What else shall I say? Well, anyway, so ask me if anything is unclear for hints or whatever. I'll be happy to comment. Basically, all of these exercises are related to what we did last week and what we'll do today. In some case, applications, in some case, related results, in some case, limitations. Exercise number 6 shows common misconception that whenever you take a free filter and take a reduced product of algebras with respect to it, excuse me, free filter, that you get countably saturated algebra. That's not true. This is one prime example for that. Okay, so let's move back to the course. Oh yes, one more announcement. So Said scheduled tutorials for today, Mondays, from 1 to 3 p.m. And here you have Zoom meeting ID and passcode. To the course page, I just posted the meeting ID, and I just thought posting passcode would not be a good idea, but I'm going to post this recording, so passcode is technically going to be posted there, but I guess the trolls would have to go through some trouble to get it, so it's probably okay. All right, so if there are no questions about what we did so far, and as always, you're welcome to ask questions. I'll just open the chat window so that I can see if there are any questions. I'll move on to what we did last time. So this is just a reminder, basically, what we finished the last class with, a couple of definitions. So first one is the definition of a degree 1 condition over a C algebra C. It is an expression of this form. So here we have a polynomial of degree 1 in variable x, whose coefficients belong to the algebra. And on the right-hand side, we just have a positive real number. So condition asserts that when you evaluate this polynomial at your element, you get exactly norm is equal to R. And when condition is satisfied, well, it's just a natural definition. Another definition of a type or a degree 1 type. Well, degree 1 type is a set of degree 1 conditions. We'll just be looking at countable types. More about that later. And type is realized in C if there is a single element in the unit ball of the algebra, so that all conditions are satisfied by that single element. Another important notion, when type is approximately realized or satisfiable, again, in this algebra, if for every finite subset of the type and for every epsilon greater than 0, there is a single element in the unit ball, so that for every condition in that finite subset, we have that if we compute the norm of P of B, well, it may be off by at most epsilon, actually by less than epsilon from R. And such B's are called partial realizations of the type. So clearly, if type is realized, it is also satisfiable, but vice versa need not be true. For example, you can look at it something like this. Let me just add one more page. Oops, but not there. So, for example, you can look at C-star algebra C of 0, 1, continuous functions on 0, 1, and look at a function Fn. Okay, I'm going to draw it instead of giving formula. So at 1/2 it is 0, and it is 0 between 1/2 and 1, and up to 1/2 minus 1 over n, it is equal to 1. This is 1. Okay, and you can also look at functions Gn. Gn of t is Fn of 1 minus t. So the, oops, why do I always do this? Sorry about that. Whoa. Okay. Here. So here are the Gn's. Here is 1/2, and here is 1/2 plus 1 over n. Okay, and now we can look at the type of x such that x Fn minus Fn is equal to 0, and norm of x Gn is equal to 0 for all n in n. So this is a countable set of conditions. Every finite subset is satisfied. Actually, every finite subset is satisfied by Fm for large enough n, right? Because okay, it's approximately satisfied or not satisfied, right? If you have m large enough, then Fm times Fn is going to be close enough to Fn, and definitely Fm Gn is 0. Right, so type is satisfiable in this algebra, but now if you look at the type, if it were realized, it would necessarily be realized by a function which has discontinuity at 1/2. The function would have to be 1 up to 1/2 and 0 after 1/2. And so in the algebra of continuous functions on 0, 1, this type is satisfiable but not realized. And the point of what I'm doing next is that something like this does not happen in massive C-star algebras. So whenever you have a countable set of conditions of the appropriate type, so these are all degree 1 conditions, if the set is satisfiable, then it is actually realized in the algebra. Okay, any questions? Basically, the plan for today is to prove that. We'll see. I don't want to rush it. So I'm definitely going to prove a slightly weaker theorem, and we'll see how it goes, whether we actually want to go for the whole thing. Now, before I go on, here is the last sentence. Here is quite important. You see, I defined conditions and types only in a single variable x. For many applications, you need more than one variable. And there is no reason not to define type in 2 variables. You would just have expression like this in x plus expression like that in y. And if you want 15 variables, you probably want to call them x1, x2, x3, up to x15. So basically, it's going to be a degree 1 function in all of those variables. And that would be degree 1 condition. Degree 1 type can have any number of variables. Now, again, any condition has only finitely many variables because polynomials are finite by definition. However, if you have an infinite type, it may have infinitely many variables. There is no harm in that. But again, all of my types are going to be at most countable. So I'll just be looking at types of at most countably many variables. And not even that, I'll just stick to a case when you have just one variable, because proof is the same, but you just have fewer indices to worry about. So it's the same proof, but probably easier to digest. Okay. And here is the key definition. C-star algebra is countably degree 1 saturated if every satisfiable countable degree 1 type over C in n variables for any n in is realized in C. Right, so this is, as Matteo pointed out last time, it is very model theoretic notion. However, the proof doesn't really have much to do with model theory. Only the motivation for formulating this really came from model theory, but the proof is pretty much completely functional analysis. Okay. So here is the theorem. The corona of every sigma unital, non-unital C-star algebra is countably degree 1 saturated. Now remember, sigma unital is a generalization of being separable. It just means that there is a countable approximate unit. We will lose, I mean, the proof is the same, but you can just think of algebra being separable, and you can even think of algebra being compact operators. That's really the as interesting case as anything else. Remark, well, for C-star algebra, it's not only for C-star algebra, actually much more is true, and exactly the same theorem applies to ultra products and relative commutants of separable subalgebras and so on. But ultra products actually have stronger property, and this is something that logicians would know. I mean, they're fully countably saturated. So I'll see later on. We'll go to that. But for now, we'll just have to do with this weaker notion of degree 1 saturation.
Can I ask a question?
Yes, of course.
Why non? If it's unital, would it be a problem for the theorem?
Well, if it's unital, then the algebra would be empty, right? If A is unital, then multiplier algebra of A is equal to
yes,
A.
Okay.
So I mean, basically, you just end up with something that it's not even C-star algebra.
Okay,
right?
Okay.
So
because
yeah,
the corona
other
is
than that,
a multiplier algebra of A modulo A.
Exactly, right. So the interesting case here is if you take A to be the compact operators, and now it is important here. I'm definitely talking about compact operators on separable Hilbert space. If you take compact operators on non-separable Hilbert space, that is not sigma unital. That's an exercise. So only the compacts on separable Hilbert space are sigma unital. So theorem doesn't apply to other algebras, so compact operators. But what I'm going to do right now is prove state and prove an easier result because there are quite a few tricks involved in this proof. And basically, I'm splitting it in two pieces. So I'll prove a theorem which contains some of the ideas, whose proof contains some of the ideas, and then we'll see what is more complicated. So here is the weaker theorem. So assume that we have a sequence of unital C-star algebras. Now here it is important that BNs are unital. Then the corona of this direct sum of BNs is countably degree 1 saturated. I'm not sure whether I need to remind you what is this, but I'll just remind you anyway. So first, product of all the BNs, it is set of all sequences Bn, which belongs to, okay, I'll write this for the Cartesian product. In this, such that supremum over all n of norm of Bn is finite. Right, so you can think of this as L infinity product. So this is the product, and the direct sum of Bn's is those sequences in direct product such that if I compute these norms, they actually converge to 0 as n approaches to infinity. I should say that not everybody agrees that these are good notations, but as long as you know what I'm talking about, I guess it is hopefully not too bad. So this is the direct sum. You see, if Bn's are unital, then this direct sum is sigma unital, because I can just take something like En to be sum for j less or equal than n of the unit for Bj. Right? These are projections. These are projections. They all belong to this direct sum, right? Because norm is eventually 0. And they do form an approximate unit for this direct sum, and that approximate unit is countable. So this shows that this is indeed sigma unital algebra, and the multiplier algebra of the direct sum is this direct product of Bn's. So the corona is the product of Bn's modulo the direct sum of the Bn's. So you know, this to some of you at least, this is familiar special case of what is called reduced product. To have product of algebras, and then you're reducing it by some sort of an ideal, which is of this form. In the homework, question number 6 is basically asking you to prove that another reduced product by a free filter is not countably saturated. So there is something non-trivial going on here. These reduced products are not automatically countably saturated. Anyway, so what matters is that this is a special case of the main theorem you want to prove. And let's see how the proof would go. It's just what I said, right? So C is product divided by direct sum, and I'll use P to be the quotient map. So pretty much everywhere, P is going to be quotient map. I may need to compute the area of a circle every now and then, but I guess it's going to be clear which P is P or pi. Okay, that's a quotient map, and here is a fact. If we have a sequence Dn in product of Bn's, by the way, you can see here that I'm using a notation that is favored by analysts and maybe loathed by logicians. So by this Dn, I mean Dn for n goes from 0 to infinity. Basically, whenever the range of the index is clear, I just don't write it. So whatever is clear from the context, I just don't write it and hope that indeed it is clear. So anyway, so if I have a sequence in this product, then its norm is just the sup norm. Right, so this is an important thing to remember. If you're talking about operator norm, if you are on orthogonal spaces, the operator norm of restrictions to those spaces is the sup norm. And the norm of the image of a sequence Dn under the quotient is lim sup of the norms of Dn's. Now, why is that so? Well, remember, I defined that approximate unit En in the previous on the previous slide. So what is the norm of P of Dn? Well, it is limit as n goes to infinity. Yeah, okay. This is going to look ugly, but oh yes, it's going to look very ugly. So actually, let me call this index E sub m, and m goes to infinity. 1 minus em times this sequence Dn. So okay, so maybe here I should write this. right? So this is the quotient norm. So it is just the distance of the element to the ideal, and it is easiest computed this way. And in other words, what is this saying? Well, I'm just chopping off first 5 remaining coordinates and just looking at what is norm of the tail, and those norms form a decreasing sequence which converges to the norm. Okay, so we have simple formulas for computing norms for both the dn and its image under the quotient map. And now we can proceed with the sketch of the proof. So first, fix a satisfiable countable degree 1 type T of x. And now what does that type look like? Well, it is a countable sequence of conditions. Norm of Pn of x is equal to Rn. So here Pn is a star polynomial over C. By definition, by what is stated, it is polynomial of degree 1, but degree 1 is not going to be relevant at all. Proof is just going to go smoothly for an arbitrary degree of polynomial. It will not make any difference here. Right, so these are conditions. Now let's just draw a picture here. So here is our C, the corona, and here is, just need to be careful because my iPad is reacting in unpredictable ways when I touch certain points on the screen. So here is product of bn's. Now, if I have an element here, let's call it little a. Here I have quotient map P. Well, I can lift A. I'll use tilde for lift. Now, lift is, of course, not uniquely determined. There is a whole uncountable set of possible lifts. I just lift it somehow. So, all right, so I can lift any element. Sometimes it's going to be important to lift element while preserving some of its properties. But in this case, that's not going to make a difference. Now, what I also need to lift, well, you see, I have this entire polynomial, Pn, and Pn, you can think of it as an element of the ring C of x, right? So this is a ring of polynomials over the algebra C, and here is product, I mean the original ring of which this is a quotient. Well, I can lift all the coefficients of Pn, and when I lift them, just put them back together into a polynomial, and what I obtain is a polynomial over the original algebra, the multiplier algebra. And you can think of this polynomial as lift of the polynomial downstairs. Right, I'm not saying anything complicated here, right? So just basically lift it coefficient by coefficient, lift them all up. And what I really want, instead of working in the quotient algebra, I'll be working in the multiplier algebra with these lifts of polynomials and with other lifts. So here it is. Right, so we're lifting coefficients of each Pn to here, and Pn tilde is polynomial over this that lifts Pn in the sense that I just described. Okay, so now because we have here the formula which describes what norm works, you can now write down what exactly are we aiming at. Right, so we are trying to find a single element b, so that for all of these polynomials, if you plug that b into those polynomials, Pn tilde, this lim sup will be exactly Rn for each n. Okay, and now here is one of the key ideas. We need a nice approximate unit. This is going to be a recurring theme both in this theorem and in the next theorem. Now, in this theorem, it's easy to find that nice approximate unit, and it is really nice. So these are actually the EJs that I just described a couple of minutes ago, right? So just take some of the units of BNs for the first J BNs. These are projections. they form approximate unit. And they also have this here, this property. Sometimes this is called the monotonic approximate unit. So EJ is less or equal than EJ plus 1. Remember, for projections, what that means is that if I multiply EJ by EJ plus 1, I just get EJ. And from the formula, it is actually clear why is that so. So literally increasing sequence of projections, which is approximate unit. And the most important property is the last one, that each EJ is in the center both of the original algebra and of the multiplier algebra. So this property makes the proof of this theorem incomparably easier. So just think about it this way. So the elements of this multiplier algebra, product of m, b, n's, they're really block matrices. So here is what happens in B0. Here is what happens in B1. Actually, okay, I'll call it D0 and D1 because B's are going to be important in the proof. I don't want to cause confusion. D2 and so on. So they're just block diagonal matrices, and there is no interaction between different coordinates. I'm just restating the assertion that all of these EJs are central, right? And that's going to make a huge difference. Okay. So now finally, right, our assumption was that our type was satisfiable. So we use the assumption. So for each n, we fix this b tilde n. So I'm lifting it already. B tilde n is in the unit ball. Remember that was part of the definition of the multiple algebra, which has the property that if I plug it into any of the first j conditions, I just compute pj of b of n, then the norm that I get is within 1 over n of rj. Right, so this 1 over n doesn't matter. Any sequence convergent to 0 would do. And I'm, as you can see, I'm stating this not in the corona downstairs. I'm stating it upstairs in the multiplier algebra. Right? That's why I have this quotient map here. Okay, so we have these approximate realizations of the type, and they are all around the place. Just remember that example from continuous functions on 0, 1, right? We have these two orthogonal families of functions, and now BJ, these partial realizations, are functions which act as a unit on the first part and annihilate the second part. You just cannot put them together, right? So there is no way to put them together. But in this case, we can chop up these BJs and assemble them back, and as if nothing happened, this result of this surgery will satisfy the type. Okay, so how do we do that? Well, here's the key fact. We can find an increasing sequence, M0, M1, and so on, of natural numbers, so that for every n and for every k less or equal than n, we have the following. So let's just read this formula in the right order. Here, we are computing pk at b tilde n. Right, so k is less or equal than n. So just think of it as you know, we're looking at b tilde n, and we compute these polynomials pk. Right, so we already know from here what the norm is, but what this tells us is that that norm getting close enough to rk actually happens between emn and emn plus 1. Right, so we have m of 0, m of 1, m of 2, and now between m of 0 and m of 1, b tilde of 0 works up to, oops, actually 0 is a bad idea, I guess. Let's start it at 1, or just add m plus 1 here. Right? We don't want to divide by 0, right? So this wasn't an issue with the proof, really. So b tilde 1, I'll just start with m1 here. B tilde 1 works here. B tilde 2 works between m of 2 and m of 3, and so on. Note, by the way, that I'm skipping some coordinates. There are finitely many coordinates that I just basically throw into waste basket, because they may just be terrible. Remember this fact that norm of pj tilde of b tilde n has the right value. Rj means that lim sup of the appropriate conditions is equal to Rj. Basically, what that means is that at first finitely many coordinates, any nonsense can happen, but eventually we stabilize. So how do I construct a sequence as claimed here? Oops. Sorry. Here. Yeah. How do I construct a sequence? Well, just look at, let's see, which one is the first one. So we need to look at p tilde. Right, so as I said, we have to start at 1 now. P tilde 1 of b tilde 1. And now, what is this? Well, this is certain sequence dn for n goes from 0 to infinity, and norms of dn's have the property that maybe limit doesn't exist, but lim sup is at most R1 plus, okay, in this case it's 1 over 1, and lim inf is at least R1 minus 1 over 1. Okay, this was a bad choice of constants. So basically from some point on, we'll get the values to be in the right range. So we just want to choose M1 large enough so that the supremum is not too big. And then just choose M2, just weight enough so that the norm of this dn jumps enough above Rn minus 1 over n. And we know that we can get that. Right? And so if we have chosen mj up to some k, if you know what mk is, then we just compute, look at all pj of b of k with tildes, right? So norm of each one of these is approximately Rj. And now for each pj, I can find a big enough index so that the norm is stays big enough, and just take maximum of all those indices. But there is one more thing I need to do. You see, I have to worry about the next item and the next index, so the b tilde of k plus 1. How does it fare? So I have to increase my mk plus 1 a little bit more to make sure that these values are not too big. Right? Because the norm is supremum norm. So basically, if you're too small, you can increase it, no problem. But if you're too big already, you're dead. So that's why I need to just stretch this mk plus 1 a little bit to cover all these peaks, all the places at which this norm is too big. And if I do that, then I'm good. Right? So this was a sketch, but again, this is proved in the book in some detail. I just believe that lectures are really where I should give you intuition. Right? So basically, by doing this, we can find the sequence so that each one of these finitely many conditions is satisfied in the appropriate intervals. Any questions about this? Let me know if this is not clear. You see, my problem is that I overpassed, I don't know, 25 years. I went to one version of this proof for another, probably once a week, more or less. So I basically, I've seen it too many times. And if you're seeing it for the first time, it's probably not as trivial as it seems, as I'm trying to make it seem. So just let me know if something is not clear. Okay, so we do this, and now what do? Well, we just use these approximate unit, these differences, to chop up different bn's, right? So between 0 and m of 0, we just don't care. We don't do anything. We just put zeros there. Between m0 and m1, we just use b tilde, right? So I'm again doing it. Between m1 and m2, we just use b tilde of 1. Right, so that's this is really em1 minus em2 minus em1. Between m2 and m3, we use b tilde of 2. And between m3 and m4, we use b tilde of 3, and so on. Right, so we're just chopping up these. And now remember, all of these EMs are central. So they're commuting with all the BJs. They're commuting with all the coefficients of all the polynomials. So nothing is affected. We don't have to worry about anything non-commutative in this proof. Although the algebras, BJ themselves are non-commutative, but all the non-commutativity is happening inside these blocks. So you just don't have to think about it even. So we just chop up these and put these together in b tilde. And now the point here is because these EMNs commute with all the coefficients of all of these polynomials, we have that EMN times Pj tilde of b tilde j is just the same as Pj tilde of EMN of Bj tilde. Right. So the approximate unit just goes through everything, and we don't need to worry about anything non-trivial in non-commutative way. Right. So these polynomials are equal to this, and then if you just remember the way that the norm is computed, then this b, which is p of b tilde, and now we go back to the quotient, right? P of b tilde, if we compute pk of b, the norm of this, it is going to be exactly lim sup as j goes to infinity of the norm of pk of b at the sorry, no, actually, the way that I'm writing it is I put this in index, right? So pk of b, this is an element of this product of bn's. So just look at j's coordinate, it's lim sup of this, and that is exactly equal to rj because we chose it so that in the nth block, it is staying within 1 over n of rj, but also we are making sure that in each one of those blocks, it is big enough so that lim sup is indeed attaining rj. Right, so we have to worry that this norm is not too big and that it's not too small. Okay, any questions? Remarks? All right. So here are remarks. So first, we did not need the assumption that these polynomials are of degree 1, right? And then, if you just look at this proof, you may wonder why that assumption was there at all. And also, proof shows that in this corona, arbitrary type, which is quantifier free type. If you know model theory, you know what it is, what it means. If not, we'll come back to it later on. But basically, there is a much wider variety of countable types that have this property that if they are satisfiable, they are realized in the algebra. What is not obvious is that algebra is even countably saturated, which means that you can add types which involve quantifiers, soups and infs over bounded balls on the algebra. But proof is a bit more complicated in that case. Right. So these algebras have much stronger saturation properties. All right, so let's go back to the main result, that the corona of every sigma unital, non-unital C algebra is countably degree 1 saturated. So here we have just algebra A, think A being separable, and we look at M of A mod out A. Now, in this proof, we need some non-trivial facts about C-star algebras. First one is a very important theorem of Bill Arveson.
Sorry.
Yes, sure.
Can you point out what is the difference between this result and the one you just proved?
Yes. So if you take A to be compact operators,
yes.
This is not of the form direct sum of b's.
Okay. Fine.
You see the picture. I mean, the picture is, in previous case, you had B0 was here, B1 was here, B2 was here. So, and you had zeros off diagonal. So your operators looked like block matrices, diagonal block matrices. And in case of compacts, you see there is a problem that here we have something, and that something is annoying. So you see the salient point why the previous proof was so easy was that we had that approximate unit consisting of projections, which had a property at En times Pj of B was just Pj of En of B. Right? En commuted everything. That's just not going to happen this time. So we have to do something much more complicated.
Okay, fine.
And that's welcome. Thank you for asking. That's also the reason why we can survive only with degree 1. Just even degree 2 is already too much to handle. All right. So as I said, we need this non-trivial theorem of Arveson, and here it is. This is a notion of quasi-central approximate unit. So what I'm doing here is slightly modified version of what Bill Arveson did. So just a remark on history. So he had this paper in Duke back in the 70s, I think in 1977, I think. And this is beautiful paper, well, like anything else that Bill Arveson wrote. It's very modest in a sense, because he really noticed, the 70s were a great decade for C-star algebras. Voiculescu's theorem was proved then, and Choi-Efros results about liftings of nuclear C-star algebras. And Arveson noticed that those proofs actually have something in common. So he wrote this paper in which he explained what that common thing is, and beautifully presented all of these results. And this definition is the core of basically the main idea, his contribution to the subject, to this subject. So suppose that A is an ideal in some C-star algebra M. I'm writing here M because I'm thinking of multiple algebra, but it doesn't matter. And think X is some subset of M. Now we have approximate unit in A. So it's just approximate unit for the ideal, not for the whole algebra. We said it is X quasi-central if for any element A of X, if you look at this here, so this is, so I introduced notation last time, the commutator of A and EM. So this commutator of A and EM in norm converges to 0 if you fix any element A of X. So as you noticed, I like pictures. So here is M, here is A sitting at the bottom, X is somewhere. So we have this approximate unit, E0, E1, and so on. And so these act as an approximate unit, right? So just to remind you, it means that if I fix any element of A, then ENA minus A in norm converges to 0. But there is also this other quasi-centrality that these approximately commute with elements of X. Now, let's see, is it obvious that these things exist? Well, just think about the case, sort of our main case. Think about the case when A is the algebra of compact operators, M is its multiple algebra, or bounded linear operators. And just think of X as having only one element, S, the unilateral shift on the basis. So this is my favorite operator, and Bruce Blackadder actually wrote in his encyclopedia book that it is probably the most important single operator. And what is the operator? Well, just fix a basis. Let's say Cn is orthonormal basis for H, and shift just sends Cn to the next, Cn plus 1. Now, it doesn't take long to see that S has no eigenvectors at all. If you have any vector in little L2, if you shift all of its coordinates, you're not going to get its multiple unless it was a zero vector. Another easy consequence of that is that if you take any projection of finite rank, unless it's zero projection, it's not going to approximately commute with shift. Actually, shift is going to move it away from itself quite badly. So you just cannot hope to get X quasi-central approximate unit consisting of projection if X contains an operator like this one. So those would have to look quite different. But anyway, so here is Arveson's theorem. It's in section 1.9 in the book. So suppose A is a sigma unital ideal in C algebra M, and X is separable or countable, makes no difference, everything is continuous. Then there exists an X quasi-central approximate unit En in A, which has an extra property such that En plus 1 times En is equal to En. So En is in a sense much bigger than En plus 1 is bigger than En. Now, yes.
Should N plus 1 be on the right?
No, they're getting bigger. They're getting bigger.
Yeah, so should it be En times En plus 1?
Oh, it makes no difference that they're commuting. Actually, you get them to commute. Really, I mean, the way that proof goes, you choose an element of the algebra which is strictly positive, which means that HA is actually dense inside A, and H is self-adjoint, positive contraction, and all the ENs are obtained from H by using continuous functional calculus. So ENs are really sitting inside the commutative subalgebra of A. Right, so did I understand your question, right? You're just asking whether En plus 1 should be on the right.
I saw the proof in the book, and it seems you're also using that they are idempotent, right?
Sorry, I'm what?
Are you using that these elements are idempotent?
They are not idempotent. No, you cannot hold for idempotent. No. No, you see, no, definitely are not. No, it's okay. There is a terminology. So I call this idempotent quasi-central approximate unit. So the unit is idempotent in this sense, but the elements are not idempotent. You see, they are positive contractions. If they were idempotents, they would be projections. And you cannot hope for quasi-central approximate unit consisting of projections, for example, even if A is the compact operators. And that example with shift shows that. That there is no no such approximate unit. Did I answer the question?
Yes, but I remember seeing idempotents somewhere in your book. Maybe I was.
You saw them at many places. I'm sure about that, but not here. Not here. No. But you know, again, I use the word idempotent. I called approximate unit which has this property idempotent, but that's not. It doesn't mean that these elements are idempotent. Oh, by the way, now that we're talking about it, so as I said before, unfortunately, there is a number of typos in my book, so it's not an exception among most math books. So I updated the errata page today. And actually, in these proofs I'm doing right now, that there are a few typos. I mean, they're not horrible, basically. If you know what's going on, it's clear what the statement should have been saying. But if you don't know what's going on, then it may be confusing. So if you're reading my book, you may want to check the errata page. And also, as I said before, I'll say it again, in case you don't have a copy, I'll be happy to share a PDF file of the book with you. Just let me know. Right. Okay, so now this is a great theorem, and I'm not going to go over the proof. It is not a long proof. It takes maybe 2-3 pages, really, but it uses GNS representations of C algebras, and I promised that I will not need GNS representations in this course, so I don't want to go against that promise. So basically, if you're a C algebraist, you may have seen this. Even if you haven't seen it, it is a very nice Banach, Banach theorem argument. If not, you can still. I'll be happy to talk about it if you want, but I just don't think that I should go in here. So I mean, in the details of the proof in the class, but basically, just take this for granted. So what matters is that X is separable or countable, and A is sigma unital, then you can find quasi-central approximate unit, and it has this extra property. This property is actually not crucial. It is really more of a convenience. It just makes it easier for some arguments to go through. But quasi-centrality is the key. Okay, so here is another fact about commutation that I am going to prove. It's much easier. So suppose that S is a compact set of the complex numbers, and F is continuous function on S. Then for every epsilon greater than 0, there is a GF of epsilon. Just think of this as delta. It's really I want to refer to this function later on, but basically for every epsilon there exists delta, such that whenever you have A and B, and as usually A and B are just elements of some C algebra, and A is normal, and moreover its spectrum is subset of this set S. So what that means is that I can apply function F to A by continuous functional calculus. Right, so if that holds, then if the commutator of A and B has norm less than this delta, then the commutator of F of A and B has norm less than epsilon. So yeah, so let's see why is this true. Yep. So I'm never going to learn where am I supposed to hit. Right here. Okay. So basically proof is first just look at the case if f of x is just a polynomial and polynomial x to n, then by induction you can prove that the commutator of A and B is at most, is it n or is it n plus 1? Let's see. I think it's n plus 1. Norm of A, norm of the commutator. So that's basically by standard like what's called telescoping argument, you can get this, right? So if f is a monomial, we have our constant. Now, if f is a polynomial, the result follows. You can just add up the coefficients. So this is case 1, case 2. So if f is a polynomial, but actually what I want really is a star polynomial. So it is linear combination of x to n's and x adjoint to the n's. The previous part applies to adjoints as well. So just apply this term by term and get constant to be something like sum of coefficients. So at nth coefficient is multiplied by n plus 1. So I think it was n, but anyway. So just apply 1. And finally, in general, just use Stone-Weierstrass theorem. Right. So just basically see how small is your epsilon and approximate f by a polynomial p up to something like epsilon over 4, and then see whatever works for polynomial and just add up. Right. So this is not a surprising fact. And I should say there is a shorter proof if you like alpha products. Just assume this doesn't happen. Fix an epsilon, find counterexample, and just take alpha product, and you get a contradiction that you have two elements which are commuting, and yet function of one of them is not commuting with the other one, which is a contradiction. But anyway, so we'll need this. We'll need this only for one function, for function f of t square root of t.
Do you need that a has norm less than 1?
Good point. I might. Yes. I guess you're right. Thank you. Right. So you know what? I'll just say that S is subset, because again, I just need this function on there. So let's say that S is subset of the unit disk, so that norm of A is at most 1. Thank you. Yeah. Okay. Sorry. Right. Okay, so now we can finally go back to the proof. So we have M of A mod out A. So just like in the previous more specialized theorem, we fix a satisfiable countable degree 1 type T of X, and it's enumerated as a countable set of conditions, Pn of X equals to Rn for n in n. And just like before, we lift coefficients of each Pn to the multiplier algebra. So Pn tilde is polynomial over, this is not this, this is M of A that lifts Pn. And just like before, for each n, we fix this approximate realization in the unit ball of M of A, so that the first J conditions are realized up to 1 over n by that B of n. And so far, this is identical to what we did before. Okay, and now we have all of these coefficients to worry about, and now let xj be the set of all the coefficients of Pn and all the Bn's for n less or equal than j. So xj is a finite set. And x is the union of all those finite sets. So it's countable. And because of that, we can fix an x quasi-central approximate unit of A, which has this idempotence property, En plus 1 is En is equal to En. Now, Arveson's theorem does not tell us what is the rate of convergence of of these commutations to 0. But of course, we can just speed up the rate as much as we want by going to subsequence. And we're going to do that. We want these to converge really, really fast. So here we are. Right, so this is G. G is this function from the previous, from that last lemma. As function pointed out, we need to know that the norm of A is at most 1, but that's fine because that's really what I care about here. So look at this G square root function restricted to interval from 0, 1. And so for every C in Xj, for every j, I want this element of approximate unit to commute with C really well up to, see, this G square root restricted to is of 2 to minus j divided by 2. Right, so we just speed up this sequence. And now we do something to this sequence. So this is a formula that you see quite often in subject, goes back to Arveson's paper. Fj is Ej plus 1 minus Ej to 1/2. Note, Ej plus 1 is greater or equal than Ej, which means that this is a positive operator. It's positive contraction, which means that by continuous functional calculus, we can take its square root. So Fj's are square roots of those. And E minus 1 is just 0. And now we have a few claims about this sequence. So first claim is that for each n and n less or equal than j, this Pn tilde of Fj Bj tilde this Bj should be B of j tilde. You see, I have this convention that B sub j means element of a sequence, but here this is the jth element in this. So here it's also B tilde of j. Okay, so why is that so? Well, that is just by the choice of EJs, right? You see, because I had this over 1/2 because if EJ commutes up to some point with our element and EJ plus 1 commutes up to that same point, then their sum converges up to 2 times that quantity, which means
here you're using the degree 1 condition.
Exactly. Yes, that's right. That's right. I'm using degree 1 condition because these polynomials, right? So what is Pn? Pn of x is something like x a1 x a2 plus a3 x star a4 plus some a5, right? So I don't have to worry about the exponents here. All that is needed is to commute with these guys here, right? Thanks. Right. So so basically, what it shows is that up to 2 to minus j, these are all the same. Now looking at these formulas, it may be that I wanted to be very precise. Maybe you need some other function here. Maybe g's for square root is not enough, but I guess it's clear that you just see how much you want them to commute, and you just assume that they're commuting sufficiently well. Anyways, so the first thing is that this and this and these are all the same. And you may be wondering, why am I bothering with first two? Because you see in the previous proof where our approximate unit was central, I just had this, right? Everything was just multiplied on one side, but this putting B between FJs is going to be important in a moment. Okay, so now next fact is if I take sum of Fj squares, then this is an infinite sum, but that infinite sum converges in strict topology to 1, and by 1 I mean one of the multiplier algebra. All right, so that's consequence of just the definition of FJs. Just the point is that strict topology, if you have any element of the algebra A, because EJs form an approximate unit, from some point on, En for large enough n times your element is going to be essentially equal to that element. So that after some point, this semi-norm given by that element doesn't contribute anything. So this infinite sum indeed strictly converges to the identity. You can just check that this difference of this and the identity converges to 0. Difference of partial sums and the identity converges to 0.
Ilijas,
all right. Yes.
Can we expect Fj or Fj squares to be orthogonal?
No, we cannot.
No.
That's exactly the question, right? So,
Okay.
The only way, okay, look, they look like this, right? So this is F0, this is F1. They form partition of unity, right? This is F2. So the only way they could possibly be orthogonal is if they were projections, right? So spectrum of any Fj is subset of the unit interval, and if it's not equal to, I mean, if there is anything in the spectrum T which is between 0 and 1, it means that some other Fj is also non-zero at that very place, which means they're not orthogonal.
Okay.
So this is exactly why proof is a bit more complicated than the first proof, that things are overlapping. Thank you for the question. Yeah. Okay, so this was second entry. Now let's take a look at the third entry. For every Aj in L infinity of A, this sum Fj, Aj, Fj strictly converges to something, and it satisfies this norm estimate. So the norm of this is at most sup of the norms of Ajs. Now that is very important and somewhat tricky. So let's take a look at why that is true. There was supposed to be a pause right here.
Excuse me.
Yes.
But the EJs are self-adjoint or not?
They are positive. They are positive elements. Remember,
okay.
in my so they are all positive contractions of norm 1.
So they are not projection, but they are self-adjoint and positive.
Yes, exactly. So in case of compact operators, these are going to be some finite rank operators which are positive contractions. So essentially, something whose spectrum is subset of 0, 1, and they're going to be flatter and flatter with respect to x. Right. So I want to prove number 3 here. Okay, so now the sum strictly converges. Why is that so? Well, exactly for the same reason why number 2 strictly converges. What is important here is, yeah, okay, so sorry, let me just say something. So without loss of generality, sup of the norms of Ajs is finite, right? So if it's infinite, then actually sum doesn't strictly converge. So strict convergence falls from here in the same way as in the proof of 2. But now we need to see why we have the norm estimate. So what I want to prove is that norm estimate holds for all finite partial sums. So for every n, if I take sum j less or equal than n of fj, aj, fj, this is at most, actually let me just call this k so that I don't have to copy it several times. This is at most k. Okay, and in my book, this is done by using Unital completely positive maps. It's a standard proof, but I just yesterday actually found this clever trick in Vern Paulsen's book. So it's definitely a great book. Oh, hold on. Did I put right? Yeah. Okay. So here's the proof. So this sum. I can represent in the following way. Consider the following matrix. Put F0, F1, F2 down to Fn. In the first row of matrix, this is m plus 1 by m plus 1 matrix, and everything else is 0. Then multiply this by diagonal matrix that has A0 through An on diagonal. And then one more term in the product, multiplied by the transpose of the first matrix, F0, F1, down to Fn. Okay, let's hope that I got this right. So if you multiply this, what you get in the first row, you get F0, A0, F1, A1, F2, A2, Fn, An. When you multiply by this, you get exactly matrix that has our sum j less or equal than n, fj, aj, fj, and this is the top left corner, and everything else in the matrix is 0. Right, which means that the norm that we are trying to estimate, this norm here, is equal to the expression is equal to its product, but the norm is by submultiplicativity bounded above by the product of these three norms, right? So the norm of our sum j less or equal than n, fj, aj, fj, is at most, okay, since I'm lazy, I'll just call these matrices, let's call them A, B, and C. So it's less or equal than norm of A times norm of B times norm of C. Now let's see how can we estimate norms of these matrices. Well, B is fine, right? So norm of B is exactly the maximum of the norms of the AJs. Right, it's diagonal matrix. So it's three norms of A and C that we need to worry about. And this is where the clever trick comes. So what is norm of A is, actually norm of A squared, is the norm of A star, the C star equality. Of course, for matrices, right? Matrices are C star algebras. But what is A star? Well, it is just matrix that has sum of Fj squared in the top left corner, and everything else is 0. And this is sum of Fj squared. This is a positive operator that is less or equal than 1. Forgotten one. Right, so it's less or equal than 1. Similarly, the norm of C squared, now we just go the other way around, C star C, and this is again going to be actually the very same matrix, right? And it's less or equal than 1, right? So if you put everything together, this is less or equal than maximum of the norms of AJs. Okay. All right. Now I just have to go back to this here because I forgot to put pauses here. So let's see. So we proved 3. Now we move on to 4. So what 4 says If you look at this sum that we now know it converges strictly, and we have an estimate, upper estimate for its norm. The norm of its image under the quotient map is just limit as n goes to infinity of, I forgot p here. No, I didn't forget. Limit as n goes to infinity of these sums of tail ends of this infinite sum. Right. So why is this true? Well, it is just a definition of the quotient norm. Right. So this is really the norm is the distance to the ideal, and this is the distance. And there is just one more property to check, that if, in addition to all that, we have the following property, that the norm of aj and norm of aj times fj squared, that difference between those two converges to 0, then the product, there is norm, the norm of this quotient image under, the image of this infinite sum under the quotient map is at least lim sup of aj fj squares. Okay, so let's try to wrap this up and see how it all works together. Okay, I need to prove 5. Now, what is the issue with 5? Well, you see, let me add a page here. So you see what the trick here is. Well, we want to make sure that the norms are as that they are supposed to be. And just a second. Oh yeah, right. So the proof of 5. What do we have? Oh, by the way, actually, more importantly, this lim sup, because these differences converge to 0, this lim sup is also equal to lim sup of the norms of AJs, which is really what we want. So what do we do? Well, for each C, for each n, actually before that, so we may assume that A is a subalgebra of some B of H, right? Because this is a C star algebra, we can just represent it on some Hilbert space H. And now, just fix Cj in H, unit vector, such that the norm of Aj fj squared Cj is approximately norm of Aj. All right, so you just have to do this up to some epsilons and deltas, but we'll just do it. I'll just write approximately. Now, what we want to prove is that even if I take this entire sum AJ, actually I shouldn't be using J here as an index because J is used. Let's say sum K, AK, FK squared CJ. So I want to estimate that this norm is at least AJ, the norm of AJ. But now, what is that norm? Well, it is greater or equal the norm of AJ, FJ squared CJ minus norm of everything else. Okay, but now this is actually the place where we need this fact that FK, not FK, not FK.
Do you mean CJ rather than CK?
I do mean CJ, thank you so much. Yes, yes, of course. Thank you. CJ, yes, thanks. So remember, we had this property that EK plus 1 times EK is equal to EK. How does that translate in terms of FKs? Well, it means that FK times FL is going to be 0 if K minus L is greater than 1. Right? Any two of them which are sufficiently far from one another are going to just be annihilated by each other. Right? So just basically it's partition of unity, and only the adjacent elements are overlapping because they are sharing one of these EIs. So what that means is that this infinite sum actually is just sum of two of the elements. And now here is another fact. You see, there is a little argument here. Let me. This here.
Sorry, can you
Yes.
explain this inequality? I'm a bit puzzled by this.
Oh, it's triangle inequality.
But what? Why?
All right. Well, I'm taking out one of the elements of the sum.
Yes.
Right. And here, this is everything else. Right. So this plus this without the norms is equal to this. So the norm, I mean, just that norm of A plus B is at least norm of A minus norm of B.
Okay,
That's
fine.
triangle inequality. Yes. Right. Now, back to this here. What this implies is that Fj squared Cj is actually very, very close to Cj. Why? Well, Fj is a positive operator of norm 1. So you see what, let me just interpolate. What this does imply is that norm of Fj squared Cj is very close to 1. And now it is an exercise that if you have a positive operator of norm 1, if it sends a unit vector to something that is very close in norm to unit, it has to be very close to the original vector. And because of it, you have this here. But now, what does this mean? Well, remember, because sum of all the Fk squared is equal to 1, it means that if I hit Cj with any other Fk squared, what I get is roughly 0. Right? Because there is nothing left there. So this here is approximately 0. And because of this, I get this inequality here. Because of that, right, so this lim sup is going to be at least equal to lim sup of AJs, right? So just applying this to each AJ, choose AJ whose norm is close enough to this lim sup, and just see that late enough this norm is still big enough.
So why
Why
is the norm of fj square of cj close to 1 again?
Oh, because of this. You see, this is so okay. Let me write it here. So AJ, norm of AJ eta is at most norm of AJ times norm of eta, right? And we know that norm of AJ fj squared of C is close enough to norm of AJ, right? So so if norm of fj squared C was small, if it was a bit less than 1, then then it wouldn't be, right? So this is right now. So AJ fj squared C, I forgot to put do not disturb sign, CJ, so this is at most norm of AJ times norm of fj CJ. Right? So if this is smaller than 1, then this is going to be smaller than norm of AJ. But the assumption was that they are close to one another, right? That's here. Right, so I'm choosing one of those.
Okay, I see. Thank you. And it's automatically smaller than 1, right?
Which one is smaller than 1?
The norm of fj
the norm of what?
square. The norm of fj square of cj.
Well, it could be as big as 1. I mean, if it could be 1. I mean, if it's basically fj is a positive contraction of norm 1, so it probably has some eigenvectors. So actually, if you're lucky, we just choose cj, so that fj squared is cj is equal to cj. In which case, these terms here at most one, exactly, yes, right. So we have this. And now we just need to put everything together. Wait, what am I doing? Right, okay. Just scroll. Right, so this was the other proof. And finally, hold, this makes no sense. So oh yes, right, sure. So replace. Okay, this is said in a horrible way. Replace EJ with a subsequence such that with FJ defined as before. So FJ is EJ plus 1 minus EJ to 1/2. That this is within Rn. What do I mean by this? Well, this is analog of what we did in the product case. You see, we know that Pn tilde of Bj tilde, the norm of this, the norm of the quotient of this is close enough to Rn. Now, what that means is that if we go to a faster this sequence of this approximate unit, we can make this norm as close as we want to Rn. Exactly the same as we did in the product case, right? So so basically all of the arguments that we had before work for sequence EJ, but also if you go to infinite subsequence and redefine the FJs, everything still works. And you just want to make sure that for each Bj and for each n less or equal than j, the norm of this polynomial is actually basically attained up to 1/j inside below each one of these pieces of the partition of unity given by the FJs. And now we just take, as before, B to be the image under the quotient of this infinite sum. This is in the unit ball of the multiplier algebra. And finally, if we compute what is the value of Pn at B, it is going to be this, and this is equal to this norm, and that is equal to Fj, so B realizes the type T. So again, this is a quite complicated proof. Trying to present it in a class was a bit optimistic, but you can take a look at the book, and I'm happy to talk about details. I should say again that there are some typos exactly in this part of the book, so you may want to look at the errata page as well for that. Okay, any questions? And thanks to Function and to Matteo for asking questions. So I definitely appreciate questions. I guess it's really important that you ask if something is not clear. Okay. So if there are no questions, then I'll just remind you that Said is having tutorial today. At 1 p.m. Right, you have a Zoom link, you have a password, and we'll continue on Friday. So let me know if you would like to see more details of this proof or anything else. But I guess that the best way to learn the proof is to essentially get some idea by talking to someone and then just sit and work through it with a pen and paper. There is no replacement for that, really. So I'm just trying to give you an idea of the intuition of what is going on here. So plan for the next time is to see what about this degree 1, how much can we get by degree 1 types, and why we cannot go further. Yeah, so that's all for today. Let me know if there are any questions. Okay, so if not, then I'll see you on Friday, and we'll be in touch. Okay, I'll stay safe. Bye.
Bye, thanks.
Thank you.